Okay, so here's part two of my ideal gas law presentation, I guess. So in this particular part, we're going to imagine that we've got some container of gas. So it could be a rigid container like this, or it could be a balloon. But that container is sealed, and so we can't change the amount of gas that's inside that container. We can't add to the amount of gas. We can't take any gas out of it. Well, if that's the case, and if we rearrange this equation here, this PV is equal to nRT equation, we can put all the things that can change on one side of the equation and leave the things that are constant on the other side of the equation. So that's exactly what I've done. I've divided both sides by temperature. And then on the right-hand side here, I've got this NR. And that NR, well, that's just the number of moles of gas that I have times that constant R. And I can't change the amount of gas present, so that's just going to be constant. So it doesn't matter how I change the pressure, the volume, the temperature. When I multiply P times V and divide by T, it always has to give me that number, that constant. That is what NR is equal to. So as a result, because of the fact that PV divided by T has always got to give me the same value, I can say that, well, if I start out with some initial pressure, initial volume, and initial temperature, and I figure out what that number is, then, my initial pressure times my final pressure times my final volume divided by my final temperature has got to be the exact same thing. So this allows me to write out this equation right here, which is a really handy equation in terms of analyzing maybe how pressure changes when I change volume, or maybe how temperature changes when I change pressure, or maybe how pressure changes when I change volume and temperature. So this is a really powerful tool. Now, we may have seen this split into three different pieces in chemistry. One of those pieces is Boyle's law, and honestly, I forget the names of the other two laws, but it's okay. We could just keep it all in terms of the equation that's boxed in front of you, and that way we only have to really remember one equation. All right, so let's see what we can do with this. So in this particular example problem, we've got a bottle of compressed air, and what we're going to do is we're going to put it on a hot stove. Do not do this, okay? But we're going to put it on a hot stove. We're going to heat it up to a temperature of 100 degrees Celsius, so boiling, I guess, the boiling point of water. We're told that the initial pressure inside this bottle is 2 times 10 to the 5th pascals, and the initial pressure was the initial temperature was 30 degrees Celsius. What are we asked for? We're asked for the pressure inside the bottle. We're asked for what is the final pressure here. We're given the initial pressure. Oops. We are given the initial pressure is 2 times 10 to the 5th pascals. We're given the initial temperature is 20 degrees Celsius, 30 degrees Celsius, my bad. Of course, we can't operate in Celsius when we're dealing with ideal gas law stuff. We have to operate in Kelvin. So we have to do the little conversion there, add 273 to that to get us our temperature in Kelvin. That's 303 Kelvin. I'm struggling here. There we go. And let's see, what's our final temperature? Our final temperature would be the 100 degrees Celsius plus 273. That would give us 373 Kelvin. Okay, all right. Let's see, what was our equation from the previous slide? PF VF over TF equals P initial V initial over T initial. Okay. So I've got the initial temperature. I've got the final temperature. I've got the initial pressure. But I've got those volumes kicking around in there. Now, okay, so maybe I'm not given enough information. Well, maybe I've got to assume something. So you can picture a bottle of compressed air there. It's probably rigid container. Volume's pretty much fixed. So the initial volume is going to be the exact same thing as the final volume. Yeah, that's going to be the same value, the exact same number. So if that's the case, we can just divide through by volume and get those guys to cancel out. All right, let's rearrange our equation, solve for final pressure. Looks like if I multiply both sides by T sub F, I will get out the result that I'm looking for. And now let's plug in some numbers. Oops, not equals, not yet. We get 2.5 approximately times 10 to the 5th pascals as a result. Okay, so that would be our new pressure inside of this container. Now, if we heat it up enough, the pressure is going to be so large actually that the bottle can't withstand the pressure difference between the inside of the bottle and the outside of the bottle, and it'll burst. So don't do this. Okay. Also, don't heat a can of green beans or any other closed can by just throwing it into a campfire, because if it gets hot enough, boom, no good. All right, so let's take a glance at this one. We've got a bubble at the bottom of this beer glass, and if you look closely, you might notice that it grows in size as it moves upwards. So now, what causes that? We might have learned, or we might remember, that as we move upwards in a fluid, that the pressure in the fluid decreases. Let's see. P, the pressure at the bottom of that glass, is going to be equal to the pressure at the top of that glass plus rho GH. So as we move from maybe the top to the bottom, and we think about what happens to the pressure, at the very top, it's going to be atmospheric pressure, and then the pressure is going to get greater and greater and greater the further down we go in that glass of beer. Conversely, that means, if we start at the bottom and rise to the top, the pressure is going to decrease. And then our ideal gas law says what? Let's see. Well, at least the modification, the comparison there. There we go. The temperature in the glass is going to be constant throughout, so we can eliminate the temperatures there. They're going to be the same. And then let's see, our initial pressure is the pressure at the bottom. Our final pressure is smaller than the pressure at the bottom. So that means that my bubble is going to have to grow as a result. The pressure decreases, so the volume is going to increase. So that's one possible reason why the bubble would grow as it ascends. The pressure decreases as the bubble moves upwards, so the volume increases. We could also have bubbles like joining together. So as we accumulate, that'd basically be us accumulating more and more gas in the bubble. And so the volume would increase that way as well. The bubble would grow. Okay. But this one here that you see on the screen is a little more interesting than that. All right, so this is a question for you. I want you to pause the video and try to work this out on your own. I will say you might find it a little bit tricky. That's okay. So let's read this real quick. It says we've got an ideal gas trapped inside a container. It's trapped inside a container with a movable piston. That basically just means that it's trapped inside of a container, and the container's volume can change, but the amount of gas inside the container is not going to change. All right, what else were we told? We're told the final temperature of the gas is 2 times the initial temperature, and the volume is reduced to 1/4 of its initial value. Okay. Given this information, what will the final pressure of the gas be relative to its initial pressure? I want you to pause the video and try to think about this and answer the question. So pause. Okay. So the way we go about approaching this type of problem is we look at the words that we've got on the screen and we start translating those words into math. This is a very important skill. So the very first thing that I see in terms of words that would translate into math, it says the final temperature is. That is there. Whenever you see the word is, that's the same thing as equals. Is what? 2 times the initial temperature. Okay, so there's a relationship between final temperature and initial temperature. What's next? It says the volume is reduced to 1/4 of its initial value. Okay, so final volume, again, is, and then what? It says reduced to 1/4 of its initial value. Oh, it is 1/4 of its initial value. Notice there it says reduced to, not reduced by. Actually, reduced by, I guess, wouldn't make any sense, would it? The volume is reduced by 1/4 of its initial value. Well, at any rate, if it said reduced by 1/4 of its initial value, it's like we're taking 1/4 of it away. So it'd be like 3/4 that we would have there. What we've got on the screen is a little simpler to think about. The volume is reduced to 1/4 of its initial value. So we've got the equation written out on the screen for that. Okay, what will the final pressure of the gas be relative to its initial pressure? Now we need our expression there, PV over T equals PV over T. Let's solve this for final pressure. We can do that by multiplying both sides by T sub F over V sub F. So I'll just draw that out there. Multiply the entire expression by T sub F over V sub F. And then what are we going to get as a result? We're going to get, on the left-hand side, P sub F is equal to PI VI over TI times TF over VF. Okay. And now what can we do? We can plug in these expressions that we have for final temperature and final volume. So let's do that. PI VI over TI. And then our final temperature is twice the initial temperature. And our final volume is 1/4 the initial volume. So I've just plugged those into that right there. All right, and then if I check out and look what I have, let's see, I've got initial volume in the numerator. I've got it, and it's going to get divided by initial volume. There we go. Those are going to cancel. I've got initial temperature in the denominator. It's going to get multiplied by initial temperature in the numerator up there. And so what I have is the end result is twice initial pressure divided by 1/4. And 2 divided by 1/4, you can do this yourself. 2 divided by 1/4 is 8. 2 divided by 0.25 is 8. So the answer is that my final pressure is going to be 8 times my initial pressure. So if you chose that one right there, you got the correct result. Okay. And that does it for this one.